I got the same email and came to different conclusions. So this will not be a summary. This will be Ted grandstanding and talking about ALMA and JWC, and then grudgingly or graciously sharing the stage with you for the last hour. But I'm the composition guy, so I'm going to stick, for the most part, in my lane. But the key part of composition is that it links to the disk physics in many aspects, and it links to the planets. So I want to try to do both, and I want to showcase some of the observational efforts that perhaps have not been seen. So key part of the motivation, right, the way I'm doing this is trying to understand how planets are born, and particularly this rock that we're standing on. But the rocky planets and the sub-Neptunes, they have very distinct aspects of their composition, right? The most defining characteristic is that they are dominated by mass by the rocks, the solids, right? And in particular for the sub-Neptune, so this is just a schematic from Schlichting and Young, but the key point is that if you have enough of a hydrogen envelope on the planet, the surface remains molten, and the solids communicate with the atmosphere. It's an open system at some level. And obviously it's complicated, but that means the disposition of the solids is central. And that's pretty obvious to think about from the perspective of the Earth. But it's an important perspective to think about from the perspective from looking at it from the sub-Neptunes, all right? And so the key carriers of our oxygen here are silicates, so the solids, and water, CO and CO2. Carbon, half of the carbon's in carbonaceous grains. The other half is in CO and CO2. And there are some instances, as we saw in the disk, where either the carbon carried by the CO and CO2 or the carbon carried by the carbonaceous grains is converted into things like C2H2 and methane in some instances. The nitrogen is carried by carbonaceous grains to some extent, but it's mostly probably in N2 and ammonia salts, and sulfur is just a giant question mark in my brain. We know that in CI chondrites it's solar, and it's mostly in FES, but in the interstellar medium we don't exactly know where the carriers are. This is my solar system slide. I put everything that I thought was useful and interesting on this slide. So one clear thing is that some material in the solar system was hot, it cooled down and you formed minerals, and some of it was cold and came in from the outer disk or was supplied from the ISM. The Earth and meteorites are carbon, nitrogen, and water poor, okay, in any sense. The D-to-H ratio in the solar system, in all water in the solar system, is enhanced. It's not just the Earth, it's all water in the solar system. There's an isotope anomaly in oxygen that is believed to be linked to radiation that is found in meteorites. Jupiter and Saturn are supersolar in carbon, nitrogen, and some noble gases. The C-to ratio was claimed to be known, but then there's another paper that says that it's somewhat different than the number that was posited in another paper. So it's about an order of magnitude uncertainty in the oxygen abundance. Ergo, we don't know the C-to-O ratio. There's a great new paper by Malamud out showing that Uranus and Neptune are dominated by methane. They're not ice giants, they're methane planets. And then we also know that the non-carbonaceous chondrites and the carbonaceous chondrites were completely separated chemically at some point, probably by Jupiter. That's the most likely thing. And as Steve reminded us, when these things form, pebbles of order the size of millimeter were present. So when is that? So this is the timing from the solar system. The condensation was the first 100,000 years, give or take. And then you have chondral production, and the achondrites form Mars. And there's your NC and CCs up there. They're forming on the order of 2 million years. Okay, and so this is sort of the timing as we know from the solar system. In terms of condensation is one process. The opposite process is for stuff that is supplied from the ISM and the outer disk is sublimation. All right? And the most volatile material is CO and CO2. That'll be in the gas, for sure, where the rocks and the sub-Neptunes are forming. The water maybe is ice, maybe is gas. And then you get to the carbonaceous material, the carbonaceous solids, which depending the pause would come off at around 300 to 400 K, and maybe the macromolecular material will break apart around 500 K. And then the refractories, 1200 to 1400, depending upon what you're looking at. And these are the things that are clearly coming from either the outer disk or the cloud. And a neat thing was this result by Zeichner showing that some of the pause in Ryugu actually had interstellar heritage. That is, they formed at less than 30 K. So that says there's a production mechanism for PAHs at very low temperatures. Now, that sublimation, that happens when things are small. When you're building up planets, other things happen, which was a very painful thing for Ted to learn, but I spent a decade on this. So there's, when you hit the planetesimal stage, you have the 26 aluminum heating that can lead to you devolatilizing, losing your water, such as in the Lichtenberg paper there. You can also lose some of your organics. There's also thermal metamorphism that can lead to some of the organics degrading into CO or CO2 that then diffuse out. And you get to planetesimals, you go to your planets, and then of course you could lose your volatiles to the core, and the ones that don't get left in the core and are not soluble in the silicate are sitting in the atmosphere, and if you got these impacts banging around, you may lose to the basically atmospheric loss. This is a true wild card in my mind. Okay. So I want to talk about the protostellar phase first. This, I think, is really, really important. It's where the accretion energy is being released, right? And so the disk, the young disk, is warmer. And if you want to think of the process of either condensation, it started hot, it became cold, or sublimation, it's hotter, this is the phase where you're going to lose the volatiles the most, right? But it also is the phase for which we know the least in terms of characterization, because AMA spent much of its time doing class 2 older disks, and James Webb is just getting going. But this is a beautiful program, the eDisk program on AMA, that looked at 12 class 0 and class 1 objects, and so those are less than a half-million-year-old protostars. Okay, the observations here you're looking at are the dust thermal continuum emission with sort of AAU structure. One of the odd things in this program is that they didn't know whether a disk was present, but somehow there's a selection flag that led them to choosing systems that were more edge on. These were some of the brighter systems, so clearly something about being brighter was related to them being edge on. But you can see there's disk, there's some sort of spiral structure in that one. This one's gorgeous, nice little pencil there. The results from this program is that there's no evidence for substructure at this age, but it could be that the dust is optically thick and it's hiding something. They were able to kinematically isolate a number of disks, but they ranged from really small to like huge, 1,000 AU, hundreds of AU. There's very little gas data that was obtained by this system, and the one case where they really looked at it, you still, at 8 AU resolution, you're looking at cold stuff that is just not getting to the scale of interest. This is that one pencil, and I thought I would show that. This is the continuum image shown as the solid outlines there, and there's the C18O distribution, and it's just beautiful. It's integrated intensity, integrated emission, that sort of amount, and this is temperature times tau, essentially. You can see the velocity distribution. There's your disk rotating. And the one, I think, really key result in this is that this particular disk has not yet settled at that age. All right. A new result, which will be out in about 2 months. This is Melissa McClure and Meryl von Hoff's work It's a gorgeous JWST spectrum of a protostar where you see all the bands of water. This is the 6 micron, and this is hotter, and then even hotter water, CO gas. There's the crystalline silicates right here. There's H2 emission lines, but the really neat thing this was the detection and direct inference of SiO gas in absorption. And this actually, as I will explain to you, is the first astrophysical evidence of condensation of solids. Now, why do I say that? Crystalline silicates have been known for years in many class 2 disks seen in emission. Those silicates owe their origin likely to annealing. In protostars, there were surveys by Spitzer. There were only 2 protostars that stood out that had crystalline silicates in absorption. But we didn't know at that time that in both of those systems we see SiO gas as well. And so this is showing the SiO gas, this beautiful band. Again, the amount of SiO relative to water was on top of the other plot, was on the order of about 10%. So that's an awful lot of silicon in the gas, all right? And here's the fit for what the solids are. So we have the interstellar silicates here. All right, that provides sort of the shape of the band, but then all these little bumps here, that's mostly enstatite or phosphorite. Hidden underneath it, maybe, is aluminum oxide that helps fit around here. And there's a possibility that silica is present in this system. Now, most of the silicates in the interstellar medium are amorphous in form, so that's another key point. So, what we tried to do is Merrill Van Hoff submitted an ALMA program to try to see if we could detect SiO from the disk. Essentially, we know the SiO is present in the system. We know its column density. We know its temperature. And we could predict that we would detect SiO at the quiescent velocity if the size of the emitting area was greater than 2 AU. Essentially, we would have seen it. And so we also put CO in the band, and we got this. I mean, when I saw this, it was this spectacular image of a protostar. So what you're looking at there, that is the high velocity CO emission. So not showing the quiescent CO at all. That's why there's a hole in the center there. That hole is not empty. It's full of slower stuff. So you see a wide angle wind, the jet, and the other side shows the bipolar lobe and all kinds. I mean, it's just drop dead beautiful. And then if you zoom in here, we see the high velocity CO, and there's the SiO. This is the spectrum. So the SiO is basically all jet. All right, and then that's in the black, and the orangish color is SO, which was kind of interesting because it actually had something at the quiescent velocity, which was like a cocoon around the protostar that we don't exactly know what that is. But the key point here is that we do not detect any SiO emission at all at the quiescent velocity, which tells us that the source size of this SiO seen by James Webb is inside of 2 AU. And we know it's condensation because you had to destroy the interstellar silicates first, make an SiO bath, cool it down to the temperature that we see SiO, and when you do that, you make minerals. And so the neat thing is, now that we have a source where we found condensation, and we have one more good candidate, we can begin to astrophysically characterize this phase and try to understand the properties of this young disk system. All right, class 2 phase, getting to some of the other things. We heard a lot about water. I don't have to show any spectrum of water, but this is work from Adrian Hauge, H-A-U-G-E, in 2024. And what he is showing, this is essentially a drift model of water. What's plotted here is the observable column density of water that is above the 20 micron optical surface. So essentially James Webb only sees material above the optically thick dust surface. So in their model, they tried to understand where that surface was so that you could sort of try to compare apples to apples. 2 different plots here. So this one has different assumptions about how the chemical timescales depend upon the mixing timescales, so the vertical mixing. The water is coming in via drift in the midplane and then viscously mixing up to the optical surface, above the optical surface. These different panels are different assumptions about the fragmentation velocity of the grains where they break apart. We heard about that yesterday. And the bottom panel is just another set of assumption about the chemical timescale versus the mixing timescale. Why is the chemical timescale on there? Because the water will get mixed to the surface, you get above that optical surface, and some of that will be photodissociated. So that means you need a constant supply if you're going to keep this going and keep any evidence of drift present. So this is the model without too much drift, with the fragmentation velocity lower. You raise the fragmentation velocity, and all of a sudden you can see just different amounts as time, okay? As time goes on, it's kind of going down like that. But interesting, you have this enhancement right at the water snow line, or maybe it's this extra material here at greater radius. Maybe that's your cold water excess that we were seeing or inferring. But an important aspect here is this requires, this assumes a source of viscosity to mix this material up. Right? And as we heard from earlier today from Alex, the dynamicists are saying, well, maybe it's alpha 10 to the minus 6. These things would require alpha 10 to the minus 3, 10 to the minus 4. So the water is telling us in a drift-dominated system that I need to bring the water up, but we don't know what's bringing the water up. The carbon explosion was the other fascinating result to come out of James Webb. And we had great talks from Sierra and Fong, sort of outlining this issue with the very low mass stars that seem to hint at some sort of evolution, that as time goes on, the disks become carbon rich, at least around very low mass stars. There's two competing theories at present for that, although they're not entirely mutually exclusive. So one is this one here, which is by Ma et al. 2023. That's the one that Sierra presented. So you have the pebbles drifting in, okay, and as they drift in, you lose your carbon, your very volatile carbon, right, because there's still carbon-rich grains present here, right? So you have your carbon-rich grains and your silicates and your water drifting in faster than the gas advection inwards. And so you get this phase where the water goes in, it's gone, and your carbon-rich gas shows up later. That powers your hydrocarbon chemistry. Important point there is CO and CO2 will not power hydrocarbon chemistry. Only methane will. And in fact, you have to remove the oxygen carried by CO and CO2 for the methane to produce the hydrocarbon chemistry. And that's an interesting little puzzle. Okay, the other model is this one here, where the carbonaceous grains are being destroyed. They are made of hydrocarbons. You release hydrocarbons into the gas, very close to the star, and that would then power that hydrocarbon formation. So Maria Majo Colmenares had a paper in 2024 where she found this star here. This is Duar 33. It is a solar mass star that has this carbon, high carbon content. The defining characteristic of this source is that it had a low accretion rate. And in fact, it's an accretion rate that was low enough to make it similar to a very low mass star. So what you're seeing here is accretion rate versus stellar mass. The gray dots here are the observations of the accretion rates for various stars. There's error bars here. You see wide scatter, but there's this well-known correlation that basically the accretion rate scales with the mass of the star squared. So it's a very steep correlation. And Majo sorted through the literature, and now we're not looking at flux over flux. This is amount over amount of CH2 over water. And you can see that, you know, on this side of the diagram, you have more C2H2 relative to the water, and then it's sort of changing shades as you go up. And so in the model that she posited is that you release the carbon at the 500 K, what we would call the soot line in the midplane. You need to viscously mix it to the surface, right? And if the accretion rate is low, some of that material can diffuse outwards. So it sort of lingers. If the accretion rate is high, it gets washed into the star. And Adrian Hogue, not to be outdone, after doing water, has a paper that was just submitted talking about that. So what does this mean for planets then in this, in either model? All right, so we have our ice line, we have our point in the disk where carbon gets released into the gas, and then our silicate front, right? Well, what is going on here, right? If I'm forming a planet here in my disk, the rocks are going to be iron and silicates with very little organics and water. We're sitting on that rock right now, right? If you go here, this is the solid state content of material from Comet 67P in weight percentage, and you can see that 30% of the solid material, the refractory material in that comet by weight, was carbonaceous, basically organics. All right. So if you're forming here, this is iron, silicates, organics, and very little water. If you're out here, you're iron, silicates, organics, and water. All right. So what does that mean? A 50% water, 50% silicate world, as posited, does not exist. All right. The solar system tells you that you can get carbon without water, but you can't get water without carbon. All right, so that's one important point. If the hydrocarbons seen by Webb are coming from carbon grain sublimation, then implies that planets forming interior to wherever that point is, in the midplane, will be carbon, nitrogen, and water poor like the Earth, because the nitrogen is coming with the organics. All right. If the hydrocarbons seen from Webb are coming from outer disk gas, then that carbon is still there in the refractory phase sitting there, and it's going to make carbon-rich worlds, of which, in terms of planets, we do not have an analog in the solar system, except for Uranus and Neptune. Now, ALMA has been playing this game of trying to think about the content of material beyond 10 AU for a while now. And this is a plot from Coco Zhang, but this relation was independently discovered by Jenny Bergner very shortly thereafter. So this is the abundance of CO relative to hydrogen versus time. So CO is carrier of the other half of the carbon. All right? And something is happening to the CO abundance on timescales of a few million years in disk systems. And, you know, I can spout on about it. I have ideas, but I'm not going to. Just something is happening to CO, and we don't know what it is. And we actually have confirmed that one problem in these systems is getting the hydrogen content. For TW Hydra, we had the detection of hydrogen deuteride, but Tomohiro Yoshida had this beautiful work using CO line profiles, and he discovered that they were Lorentzian, i.e. pressure broadening, and was able to estimate the gas pressure and density in TW Hydra and confirm that in that system the abundance of CO is very low, even inside the CO ice line. So the CO could be frozen out in grains, it's coming off. It's coming off an abundance of 10 to the minus 6. So I'm missing all of the carbon carried by CO. I don't know where it is. Or maybe I do, because now we're seeing something with James Webb. Okay. The other thing that we found is that in numerous systems, not all, but so far the majority that we've looked at, the outer disk gas appears to have carbon to oxygen ratios greater than 1. So that would imply, if it's coming from CO, that the oxygen probably went to water and the carbon sits around making hydrocarbons. And whether those hydrocarbons are in the gas or in the grains, in the majority sense, I don't know. But something's happening, okay? So these are two things that are telling us that actually ALMA is saying that outer disks become carbon-rich with time. Hydrocarbon-rich with time, perhaps. So maybe the Ma model has something going there. The last point I want to make, and this is work from Jackie Lee, looking at the mass to radius of these planets that would have this carbon content. So sort of re-looking at the water worlds here, which is the blue line. It's the line going through the center here. That's just a coincidence. This is one realization. This is where we assume that the dust to ice ratio for a comet like 57P was unity. If it's we're a little bit higher, which is probably more likely, these lines, these shaded areas are going to move down. So this is where a water world would lie, probably a little bit further down, and then a soot planet that's rock and carbon, no water, will go down closer to the Earth line. But in a plausibility sense, you know, it's likely that planets with significant carbon inventories are present. And again, in sub-Neptunes, that material will be communicating. All right, so tons of questions, but I want your questions too. We heard lots of great talks on these things. For the young disk, you know, we're at the stage now where we're going to start to characterize some things. What is the observation that we really, really need? Can we do it? We'll find out. What are the implications for planet formation, composition or otherwise, if a deep gap is present at a few AU? Right? We heard that the solar system is not very leaky at some point. Then that means that leaves that the interior completely isolated until you get to the phase that Sean will talk about later, where you start throwing things around a lot. If drift dominates and is key to planet formation, the gas will be superstellar. Right? We have very little observational evidence of superstellar gas with ALMA. But now with Webb happening, we're just saying drift, drift, drift. All right? So what does that mean for the sub-Neptunes? Well, it means they will have very high mean molecular weight atmospheres, if that were true, right? What is the source of viscosity that powers vertical diffusion that we are inferring to present? Or maybe we're wrong. Is there a distinction between planet formation around M dwarfs versus solar mass stars that leads to some aspect of a compositional change? Accretion variability. We heard a nice talk about FU Auris, right? Is that a determinative effect? The direct detection planets and Jupiter and Saturn are all metal rich. What does that mean for the inner disk? Do ice lines matter for planet formation and dust growth? I mean, I've heard all these things. You know, water is stickier. The lab doesn't show that. Water has a different fragmentation velocity than 1 year, and next year it doesn't. The only thing I know is that Hayashi 1981 said that when water comes out, you change the mean molecular weight in the atmosphere, i.e. you shift the pressure somewhat. So, okay, water is probably a pressure bump. What about other things? I don't know. Ice lines move with time, and we know that this NCCC material formed later when the snow line is inside 1 AU. Where is the water at this point? You know, did it run right in and leave you with this carbon-rich material? And if the outer disks go carbon-rich in time, is that why the CPD is carbon-rich and it's because it's so far away? And if that's true, what about CPDs for something closer in? I don't know. These are seed questions, but I am here to facilitate whatever you want to talk about. Thanks.
Great. So I am here to run microphones around, but also there are the two on the side. So we'll start here with Jack.
Jack Lissauer, NASA Ames, primarily for Laura. Let's say Ted makes one of these soot planets, which is soot and rock, and it's not in the nebula conditions under which you produce the soot and rock. It's a hot, dense thing.
Yep.
What happens to it?
Great question. Ted and I have talked about this a little bit. I think you put a lot of the carbon in the core, you outgas a lot of it, and then you have a really dense carbon-rich atmosphere. I don't know what form that would be. It depends on exactly how much excess oxygen you might have with that carbon. But you might also make some funky things like silicon carbides. But great question. I'll go with Steve.
Yeah, Steve Dash, Arizona State. I wanted to ask some clarifying questions. Did you say you can't get water without getting the carbon?
So the carbon, the refractory organics will stay in the solid state, all right, when water sublimates. So you can, when you get water with carbon, all right, always, because right, but you can get carbon without water. Just like you can get silicates without water.
Okay.
Okay.
Yeah, I just wanted to point out carbonaceous chondrites are 3% carbon and tens of percent water. So.
And comets are 28% carbon.
You have a lot of possibilities. Okay.
Yeah.
I also wanted to point out the snow line probably was outside of around 2 AU at 2 million years, because that's when enstatite chondrites.
You can play
formed.
with all kinds of models, but sure.
I mean, that's where enstatite chondrites are from, 2 AU, and at 2 million years, we know when they formed. So okay. The snow line had to be around there, yeah. And just one last comment about the snow line. I think the efficacy of the snow line as a place to form planets is simply because you can concentrate the ice and the solids there too. Kukubli had a model where dust was brought in and stranded at the snow line, or you just have vapor deposition. You built up a solids to gas ratio.
Right, that's another concept, that the water vapor diffuses backwards, freezes on the grains, and you could grow bigger things if in that.
Like the solids to gas ratio can increase by factors of 3 or 5.
But the interesting thing with the organics, they get broken apart, they diffuse backwards. The same thing doesn't happen.
Did I hear you say that Uranus and Neptune were water poor? This is Ruth Mary Clay, UC Santa Cruz. Did I hear you say Uranus and Neptune were water poor, or just that they aren't carbon poor?
They're methane rich because they have, if you take a dust-to-ice ratio of 3 to 6, then the carbon content outweighs the water content of a comet. And that the methane then sort of takes over.
So it's methane rich compared to water?
Yeah.
Or is this a bulk composition statement, or is it just?
It's a bulk composition statement. Yeah, read the Malamud paper.
Thank you.
Hey, Stephen Jacqueline from Caltech. I have I don't know if it's a comment or a question about a couple of the bullet points up here, so I apologize if this is a little bit rambly.
Yeah, and experts, please answer.
So this is in relation to connecting these disk observations to exoplanet observations that we can do with JWST and Ariel in the future. So the first point that I wanted to address, I guess, is this question of drift and how that's going to impact sub-Neptunes. So you noted that if there's a lot of drift, then the disk is going to be metal rich, and that should presumably also be the case for the sub-Neptunes that form there. And so there's some evidence for that. And by that I mean there's one planet. So GJ1214b is sort of like the archetypal JWST observation of a sub-Neptune right now. And there's evidence that it has a very metal-rich atmosphere. But moving on to a different bullet point, that planet and pretty much all sub-Neptunes we're going to get good atmospheric constraints for are going to be orbiting M dwarfs. And so I guess my question is, how close are we to understanding one of the other bullet points up here of how different are the chemical compositions of these disks around M dwarfs versus the disks around solar-type stars? Because I think that's going to be a key thing we need to do to connect the populations of planets and disks.
I mean, with ALMA, we don't have as much around the M dwarfs, right? So there's proposals in to get that data, but that's beyond 10 AU. And then you have the Webb stuff, which says that the inner disk has a slightly different defining characteristic, and the water content's pretty low, right? And so the answer is maybe.
Right.
Maybe. But, you know, the solar mass star where we do see it, we need to look a little bit more deeply and see, you know, if we can understand that part of parameter space. Yeah.
Anybody else want to weigh in on M dwarf disk compositions versus solar? No. Okay, Artem, do you have a question?
Yeah, Artem Ignishin from UC Santa Cruz. So that was a great summary. I want to make a comment and ask a related question. So this is about the 50-50 water rock take. So the comment is that when we're modeling 50-50 planets, it's definitely, we're not saying it's pure water, because pure water doesn't exist in nature as any pure substance. Mm-hmm. We're often making the assumption that water is a proxy for all the icy molecules, be it methane or CO.
That's fair.
Now, there is, in the solar system, we have Enceladus, which has a bowl composition which is compatible with a 50% icy structure. Mm-hmm. But Cassini measured the composition of the plumes, which are, if I remember correctly, 96% water, H2O. So what would be the explanation for that composition? Is there carbon somewhere else that we don't see, or?
Yeah, I would assume the carbon is somewhere else that you don't see it, or it could have been lost, because she can construct some constructs.
So would that be carbon? So are we thinking that there is too much water in the interior structure model and that there is a layer of carbon, or was that removed post-formation, or is it sequestered in the silicate core of Enceladus?
Yeah.
Of Enceladus, I don't know. Do we have icy moon people here?
Yeah.
Well, with these inner satellites, they're formed in protoplanetary disks, which have a lot higher density and warmer, so the chemistry is somewhat different. I don't know if that answers it, but you can't just look at the condensation sequences and condensation products of protoplanetary disks. The comets aren't such good analogs. And of course, the comets also are incredibly diverse. Mm-hmm. So, and in terms of Uranus and Neptune being methane planets or whatever, yeah, it's a very interesting idea. It's still very speculative, mm-hmm, and don't take that from me. This is what I got from talking with Dave Stevenson about it. Mm-hmm.
I'll definitely agree with that. You can't take condensation temperatures from a solar nebula gas and say that that is true of any other gas, right? It's very composition dependent.
Yeah, the disk itself is likely kinetic dominated. So.
Protoplanetary, not circumplanetary.
Not circumplanetary. There's a difference. Yeah.
So I have a question, Ted. How does your model for these soot planets, does it say anything about Mercury? We heard a lot about Mercury earlier today.
I always personally favored the hot formation kind of model, but I don't know. Yeah, that's for me. That's where I don't know. But we heard a lot about Mercury today, so.
Do the volatiles that Messenger found on Mercury have to be in the interior, or can they just be on the surface?
That's a question. Are they on the surface? Well, they're on the surface because that's where we're observing them, right?
Do you have a comment? You want to comment, Vincent? Mercury. I think you know more about Mercury volatiles than I do.
No, but that's a very good point. It has to be like the first millimeter. So, so that's a very big issue, actually. Indeed, it's really the very tiny layer at the surface.
So the statement is the surface is volatile rich. They're the outer surface, the 1 millimeter surface is volatile
and I think
rich.
I'm nice when I say 1 millimeter, but.
Matt, could you go to the microphone?
Go to the mic. And go ahead. Yeah.
Yeah, like I talked about in my talk with like the potassium thorium ratio, there's plenty of stuff out there, and you can go through like the messenger reviews and stuff like that where they're arguing that, and I'm not the right person to, pick their arguments apart, but there's plenty of arguments that the bulk volatiles are there as well, right? That it's in the bulk composition. So is it a ball of soot? I don't think so, but.
Yeah, I was going to point out that too, that we infer the bulk composition from the composition of the lavas, and that's pretty well established. I also wonder, though, whether we think of it as a volatile enrichment, or maybe it's just depleted in magnesium and silicon. It's easy to lose a lot of silicon to the core, and if we lose magnesium in some way, then it would look enriched, and it just isn't.
That's like the prime counter argument, right? That it's just massive amount of silicon in the core, and we're looking at it, totally wrong.
Okay. Other thoughts from today's talks? Questions related to Ted's comments or not?
Yeah.
Yeah, G.
I have a question, which is actually not related to the list that Ted provided here. So I have been having this question for a while, which is the transient event versus constant event. For example, Adolphe gave a talk on this high burst, like a high level burst of FU Ori, that could potentially significantly impact the disk structure versus those high frequency, low amplitude. Which of those will impact the plane formation more significantly? On a related note, we're also thinking about the atmospheric escape, right? And people thinking about the UV flux, the high UV, the far UV may play a significant role in eroding the atmosphere at a constant rate. However, we also have solar flares that could also have very high amplitude that could significantly erode at one shot instead of on a constant rate. So what do people think, have any investigations been done in evaluating the impact of those transient event versus the constant event on different astrophysical problems?
So I don't know, but I think it's worth thinking. The very large outbursts probably involve the disk out to about an AU or half an AU, something like that, where it gets really hot. So and then there are the extremely transient events like the XORs, which are just probably right at the inner edge of the disk, and maybe there's high energy fluxes or something like that. But there's a whole range of intermediate things that would still heat the disk to several thousand to 10,000 degrees at a tenth of an AU. So if you're interested in the tenth of an AU region, even the very small ones could do a lot of thermal heating, even though they're not huge outbursts.
Is this a comment on G's?
Hi, Vinciane Debaille, University of Brussels. I would like to come back to the soot line you defined. Would it be similar to the tar line that Katharina Loders defined a while ago?
The tar line?
Yeah.
Yeah, it's the same concept.
That would be the same, yeah, okay.
Just, Catherine looks at things more through the concept of equilibrium, whereas this would be more, I always look things through the concept of kinetics. And so the question is, the central question is, at what temperature does this happen? All right. And so in our paper, we came up with 500 K using some of the work done at Carnegie on sort of heating up meteoritic IOM. There's a laboratory experiment where they tried to match cometary organic material and made it and then sublimated it. But I think we are seeing PAHs forming in dark clouds. So up to a 7-ring PAH, coronine, was recently just detected. And the abundance from single to 7 rings, and there's a 4-ring in between, is constant. The stuff is being made in the gas at 10 K, and the only place it's going to go is on the grains. So it's likely as we have an in situ way to make carbon grains in dark clouds, maybe even in the outer disk. And so some of that stuff will get baked, make your macromolecular material, and some of that stuff won't get baked and can come off at lower temperatures. And so that's why I think we can sort of see the soot line kind of, 300, 400, 500 K, because it's PAHs.
Okay.
And that's probably where the carbon from CO went. That's my guess.
Yeah, no, but I think it would be very important because basically nothing really is happening between the silicate and the water line, but we do have another line actually in between. So that's for the modelers. Sorry about it.
Eric.
Yeah, just a few random thoughts. I mean, on the soot planets, I think this is maybe what Lauren was going to comment on, but and that is we might hope to look for indications of this, like in mass radius diagram. So if we are actually forming these silicate carbide planets, they would have a distinctive mass radius relation with terrestrial rocky planets. There's lots of caveats with that. I was also going to suggest that we maybe think about natural laboratories as ways to understand some of what's going on here, where nature is basically perturbing the system in a very obvious and predictable and observable way. And the one example I have in my head is binary stars. In the binary systems, the disk is usually markedly truncated down to 10 AU or 20 AU, which basically chops off a reservoir that would otherwise migrate eventually perhaps into the inner disk. And so this comparison between binary disks and single star disks might be illuminating. And you can think of other systems like, for example, if you're next to an O or B star where the disk is being highly irradiated and processed, that may, affect things like the CO abundance and other constituents. So that was good. And then the third sort of also completely unrelated comment was going to be that in the last couple of days I've heard some wonderful talks about how we can measure the mineralogy, or perhaps infer something about the mineralogy at the inner disk edge based on these interferometry measurements and looking for the iron to silicon abundance, the iron and magnesium abundance based on those measurements. And at the same time, we can also observe the gas, basically due to its emission, and look for signatures of depletion. And I thought how wonderful it is if we could find systems where we can combine those two and simultaneously in the same system look at the gas plus the solids and see if there's some sort of complementarity going on that we would expect, or find something completely different.
Lauren, is that a comment or response?
Yeah.
Yeah, quick response to Eric's point. The part of the mass radius diagram where the silicon carbide planets or soot planets would populate, remember that's also degenerate with planets that are just totally boring Earth-like compositions, and then you like put a tablespoon of sorry, lovely Earth-like compositions. And then you put a tablespoon of hydrogen onto them, of like, ISM type hydrogen helium mixture, and then poof, up you go. So mass radius measurements alone are never going to be the way that we find the exotic planets. Like we have to do atmospheres, and we have to couple atmospheres to interiors. So show me a spectrum that's not flat, that has some sort of feature in it, and some sort of self-consistent like coupling to what the bulk composition of the planet should be. That's what's going to convince me of a silicon carbide, et cetera, planet, or I'm hoping for a diamond planet.
The diamond is mostly where in these models it goes. So.
Yeah, you put most of the carbon into. Okay, but I actually also had a response to something G raised, right? These FU Orionis, like these really energetic outbursts, which right probably are like hugely dominant in terms of like bulk energy that these planets get to see during formation, or not just planets, but that the disk sees. And I hadn't like thought of it before now. Probably all you disk people thought of this a million years ago or learned about it in like your grad classes, but I'm slow. We talk a lot about the viscosity of disks, and Jack, very usefully gave us some nice limits on that. When there's an FU Ori outburst type thing, how does that affect the viscosity of the disk, and for how long? So that, yeah.
So it's hard to say, but you kind of try and get at at an alpha parameterization from the timescales of variability. And so when people model this, and for example, we did a thing for a small FURA outburst where we could see it first in the infrared and then in the optical. So we could see it, so we had a propagation time, right? And alpha 0.1, something like that. So, the whole idea of the outburst is that somehow you go from a low transport state to a really high transport state. And certainly in the FURI regime, the disk is way hot enough to have enough thermal ionization for an MRI, for magnetorotational instability. So basically, 0.1, order of magnitude, something like that. Jack?
Yeah, this is a technical question, maybe not relevant for specifically in the bottom line, but it's alpha h squared omega. And is it that alpha goes up, or is it that the scale height goes up substantially and the viscosity going up?
You have to have a couple of order of magnitude change in your transport, right? So you're not changing your scale height by 2 orders of magnitude.
Yeah, so no, I completely agree with Lauren that we have to be very careful about interpreting any sort of mass and radius and more information. I mean, we heard it earlier in the program in which this conference is placed. We heard a wonderful talk by Sebastian Zebu, who is using JWST to basically infer the presence or absence of an atmosphere. And so one could hope for systems where you can actually show there is actually no substantial atmosphere based on the heat distribution or the lack of heat distribution on the planet. And furthermore, you might be able to say something about the mineralogy of the surface based on the emission spectrum that JWST provides. I think for atmospheres themselves, I mean, the issue is that the chemistry of an atmosphere can be far out of equilibrium with the interior. We are on a planet, or fortunately, which reflects that. And so even without life, you could have, for example, high irradiation photochemistry driving one way far. So I would say the atmospheric composition by itself is probably only interpretable through a model which has its own limitations.
As somebody who does atmosphere interior models, I totally agree. But I think we'll move on to comments from the folks over here.
I'll just be brief, just to say that, yeah, it's exciting to think of these tracers in the inner disk that, ELTs, like the ELT and, like the interferometer, like VLTI interferometer, which has a lot more sensitivity, potentially, if we can find some tracers or, power production or changes in the temperature structure as a function of radius that shows the different dust grains changing, away from carbon or more carbon or whatever. These are things to brainstorm, I think, going next few years.
Let me talk about the viscosity issue.
I put it there because I knew the dynamicist would gobble it up, so go.
So let's start with the observations and then talk about the theory. Okay, so what do observations say about turbulent mixing? I won't use the phrase viscosity, let's talk about turbulent mixing. So we don't really have strong constraints in the inner disk, but we have some constraints from ALMA observations. Not thinking about so much the turbulent broadening of line widths, but thinking more about the dust distribution. So we know from the ringed systems that if the dust is puffed up vertically, those rings would look far fuzzier than they do. So that puts a constraint on the vertical mixing at that part of the disk, giving an alpha, effective alpha of 10 to the minus 4, slightly smaller. We have one very nice observation of an edge on disk where the constraint on alpha, because of the thinness of the thermally emitting region, which is assumed to be millimeter-sized grains at the outer part of the disk, is even stronger constraint, more like 10 to the minus 5. The thickness of that dust layer is kind of at the level of the resolution of ALMA. So that's just in the outer part of the disk. So there's some interesting constraints. Then if you look at the radial distribution of the dust in the rings, again, D-sharp survey, there's a nice paper by Kees Doulemond. So if you have a pressure bump, in principle, those dust rings could get very, very narrow as they concentrate towards the pressure maximum, where the pressure gradient goes to 0. And in order to widen those rings so that you see them, so that they're resolved by ALMA, you need some radial diffusion. And Doulemond put a constraint on alpha spreading the disk radially, or the dust radially, 10 to the minus 4 or slightly bigger. Okay, that's interesting. So if we take Ted's picture of grains or icy particles moving inwards towards the inner disk and sublimating at the ice line, and you have I think a chemical time scale of 100 years or so for the water there before it gets dissociated. Is that correct? You need to supply
the estimate that they had in the paper was 10 to 100 years, yeah. 10
to 100 years. So you need to supply the water that evaporates off the grains vertically in the disk on that time scale to maintain steady state. Then you're at alphas of 10 to the minus 2, okay, in that picture. So treat that as a constraint or as a model which needs to be tested. So in terms of actual theoretical analysis of this problem, what is it that's available to us to stir particles and to diffuse water vapor and all the rest of it? Well, I think we'd all agree that at 1 to 2 AU, there's no MRI, so we can count that out. So we have a number of hydrodynamical instabilities, which I think is fair to say at the moment are very much areas of ongoing research, and some of them being looked at more than others. So we have the vertical shear instability, which is extremely efficient at mixing things vertically and not very efficient at mixing things radially or transporting angular momentum radially. But it's thought to operate under conditions where you have to very rapid cooling. So more like out beyond 10, 20 or 30 AU, not at 1 to 2 AU. So while it's a good candidate for mixing things, like mixing water vapor vertically, it possibly doesn't operate near the ice line. We have the convective overstability, which depends on having a fairly sharp temperature gradient, which is not thought to arise in disks which are basically passively heated by the central star. There, the temperature gradient would be probably too shallow to drive the convective overstability. Essentially, it's radial convection which is driving that if you don't have the temperature gradient. And then I'd say there are two other opportunities, two other possibilities. Number one, something called the zombie vortex instability, which has not really been looked at all by the community more widely. Perhaps is something that we need to start thinking about because it operates in regions where the cooling time is quite long. so inner disk regions, and it might provide a source of mixing and turbulence. The trouble with that is you need to really hit the disk quite hard to kick it off. It's what we call a finite amplitude instability, it's not a linear instability. So it's something that you would need to kind of stimulate either by putting a planet in there or creating a vortex or something like that. And then perhaps one other, I say this somewhat tentatively, instability. If you have planets generating spiral waves inside the disk, then they can break down into turbulence in an instability called spiral wave instability. Jehan Bey showed this in his PhD thesis, that if you have a Jupiter-mass planet orbiting where Jupiter is, then it will basically generate a turbulence in the inner regions of the disk with an alpha of 10 to the minus 3. So the question is whether more embedded planets could do something similar, so which are not easily detectable and which are not generating gaps. So that's all I wanted to say about this, is just to give some perspective on the hydrodynamical side. So if anybody wants to say anything else.
Nice. Were there questions over?
Okay, yeah,
Okay, go ahead.
I have a short comment about that, because I think as a community we should not give up about the viscosity and the outer disk from the observations, because we need to be humble. We know what we are constraining is Stokes number over alpha. And to be honest, we don't know the Stokes number because we don't know the gas disk masses, also the porosity of these grains, and on top, everything depends on the dasopacity. So if we actually are humble, we don't know. It could be alpha 10 to minus 2, 10 to minus 3, 10 to minus 4 in the outer disk. So yeah, I just want to bring that to the community. We don't really know alpha in the outer disk.
So I want to come back to one of, I think, Eric's comments on learning as much as we can about the combined dust properties and gas properties at like the inner edge of the disk. And I've heard this several times this week that we don't know the gas masses very well. So what are the disks where we can find out both the gas and the dust properties really well? And can we put all of your resources onto doing that? Okay.
Because that's what we're trying to do.
Yeah, okay.
So we're trying to getting like the abundance of refractory from the magnetospheric flow. That's relatively easy, right? I mean, we just have to do models and see compared with the hydrogen. That's okay. Getting things from the dust, I mean, information from the dust is much more difficult because, well, what is the interferometric measurements that John Mania was talking about? But what we're trying to do is like model them directly from the SED. And then we only have the silicates, right? Because those are the ones that have features. And then what we know, we have olivines that could be like a crystalline and amorphous, and the peroxide that could be crystalline and amorphous. And then there are like, they have different composition, magnesium and iron, but very simplistic. And getting information from the SED is so difficult and so non-unique, right? And so that's a problem. But more, we can say, like, for instance, what Marbelli was saying yesterday, we get enstatite, yeah, because we don't have that feature of forsterite that appears, right? But also the next step is what does it mean and how do we relate it to whatever content we see in the gas? Because there is a lot of this solid state chemistry that we don't know it, and for me it's terrifying. Like for you, it's, you love it. But for me, because I really don't know. So I really would like more conversations between us and you guys and tell us what it is that we're seeing or how we interpret that kind of thing. Right? Okay.
So to complement that, in addition to emission, we can look at these so-called dipper stars where we are actually seeing either material in accretion flows or being lofted in a wind that crosses our line of sight. And there we potentially can see both the gas and the dust through the scattering properties, and then the dust through the scattering properties and the gas through absorption. And so probably the easiest thing we can do is measure gas to dust ratio. And then getting slightly harder, we can look at the metallicity of the gas. So we can get sizes of dust. So we can get sizes of the dust grains, and then through the opacity, we can estimate the column densities. And of course, a lot of the solids could be, vaporized at that point. We can use X-rays, for example, to give us hydrogen plus carbon plus oxygen and helium. So that gives us some route there to some of the more volatile things. And then, of course, we can look for individual absorption lines for the species. And that, if you are able to say something about the dust composition, then you could actually complete the budget. But I agree that measuring properties of dust and inferring composition is very difficult. And so you could basically rule out or detect exotic things like aluminum oxides. But everything else looks pretty similar, unfortunately, in the optical. But in principle, we could do that from space. And so I think we'll hear a talk from Nick tomorrow about potentially things that we can learn, not from a disk, but from a planet. But those same arguments would apply to a disk as well.
Before we go there, there is one thing that's happening, that there is a probe called PRIMA that is in phase A study. If NASA doesn't implode and it's selected, it will be able to observe the H2 ground state and spectrally resolve it and extract what is disk and what is wind. And from that, we'll be able to get the hydrogen content and measure abundances of the species we can see in the gas. And you also have access to fine structure lines of things like iron and silicon in the same spectrum, and you would really be able to start to address some of the harder points that we're trying to accomplish here.
And the mention of H2 reminds me that one space telescope that actually hasn't been mentioned so far is Hubble. And so with Hubble, it gives us access to the ultraviolet, and the ultraviolet includes, for example, molecular hydrogen, which is actually coming from the inner disk. And there we can probe, probably not abundance of hydrogen, but at least what the structure is based on the velocities profiles of the lines, because there the instruments have sufficient resolution.
If anyone still has a comment on that topic, go ahead, because I'm going to talk about something else.
Please, go ahead. Go ahead, Mary.
One last one, go ahead.
Yeah.
Just like the magnesium 2 lines that Marbelli talked about is HST, and it's the only thing, that we can really reach that is easy, that is magnetospheric. Then there are some silicon lines, but those are forming the accretion shock, and they are a real mess and very difficult to interpret because the post-shock so the easy ones would be like magnesium 2 and maybe iron 2 lines, but those are they're complicated and they are in the optical, but it's difficult.
Bennett Skinner, McMaster University. We kind of touched on this a little bit with talks earlier about the solar system, but the solar system, compared to a lot of the exoplanet populations, as far as we know, it seems quite weird. So are these aspects about the solar system that make it seem weird? Do we just happen to live in a unique solar system? If we just happen to live in a unique solar system, why do we live in a unique solar system? Or is it not unique? Or is it that these certain properties that we can measure really well in our solar system and can see are giving us information that if we were able to see in exoplanetary systems, we would realize that we're not capturing. For example, even though we might be able to see a super Mercury, we can't see a true Mercury analog as the same size in any exoplanetary system. So are we just missing a lot of things?
You minus the Mercury part out, that's my grant introduction.
I can try and give you a response from having worked on Kepler. Sometimes you hear that every star has a planet. Well, that's not been detected. It's about, among solar-type stars, roughly 50% of the stars have had, if you look at all angles, you do an analysis, have a planet that would be detectable by Kepler. It's the mean number of planets that would be detectable by Kepler if you had all the angles, you compensated for that. That's about unity. So the solar system is in this category that you wouldn't have detected any. So you have 50% of the stars where we know they don't have the planets of the type Kepler can detect. And so that's an upper bound on the fraction that can have solar system-like planets, with a little bit of an asterisk that the RV people have shown that you have to accept as a solar system analog in this case something that has maybe a Saturn or a sub-Saturn at Jupiter's location, and you could have, I don't know about Saturn's location, but the exact numbers, Lauren could give better numbers, but it's not that different. It's just not Jupiter's location. That's at the, what, 10%?
10%.
Max.
I mean, to follow up on Jack's point, I think the solar system in context thing from exoplanet data, and I'm happy to be corrected if these numbers are not good, but I often talk about, doing a little thought experiment of trying to observe the solar system from a distance. What would you see? The only thing you got a shot at seeing, kind of as Jack was alluding to, is Jupiter with a decades-long radial velocity survey. And then, so that fraction of stars that would have such a planet is maybe 10-ish%. And then the next question is, well, what fraction of those Jupiters, exo-Jupiters, have a Jupiter-like orbit, meaning wider than a certain distance and more circular than a certain number? And exactly what answer you get depends on exactly how you slice it. But it's something like 10% have an orbit wider than a couple AU and an eccentricity lower than maybe 10%. And so that puts the solar system in like a 1% minority, which is small, but not that small. And then, of course, that solar system, then in terms of the other planets, there's no constraints because you can't see any of them. But the solar systems in general can't be more common than that. I don't know, that's one way to slice it up anyway.
Yeah, just if I can briefly comment, if we're
Sure,
kind of accepting that the solar system is 1% rare or however rare, there's a lot of information that we can get in the solar system that we can't get anywhere else. So we try to use this solar system unique information to infer properties about exoplanetary systems. But if we're not representative of those exoplanetary systems, how useful is that solar system, or how representative is that solar system information?
You use the knowledge of the geochemistry and the geophysics and the atmospheric physics and the chemistry, and you predict and observe.
So on the same point, like, I would say that it's sort of like people. I was mentioning this earlier, like people are all different. There's some distribution of people. You might meet someone who's had very different experiences than the average person, but the hope is that they're still a person, and that knowing something about that. So they can still help us out a little bit learning about people.
I was just going to say that a lot of the oddities go back to Jupiter and Saturn and what they did and when they did, right? And not all of them. It would be nice if we could explain all of them with exactly what was happening with Jupiter and Saturn as they formed and grew and moved around. But yeah, some of this stuff, you can probably throw it out. If it's, Jupiter kicks something around, like maybe that's not the strongest constraint, right? But I think that's the way we need to be thinking about the problem.
And I just want to quote George Wetherill, some of you may remember, and he noted that not only is the solar system a sample of one, it is a biased sample. It is biased by the fact that there is a planet on which life can develop to the point of asking these questions.
Okay, we want to move on to comments over here that have been waiting for a while.
We change subject, or are there?
Yeah, absolutely. We've been waiting for so long, please.
Not that anything was wrong with that subject. Continue.
Okay, so I want to talk about subneptunes and metallicity, so kind of talking about the point number 3. So, in particular in the context of transit spectroscopy with JWC. So I happen to be part of the COMPASS program, which is the largest Cycle 1 program dedicated to exoplanets. PI Natasha Batalha, co-PI Joanna Teskey. And the goal of the program is to do a comparative study using transit spectroscopy of subneptunes. And so in that program, we're doing transit spectroscopy applied to 12 subneptunes. 6 of the planets have been published. You can find them on ADS. And what all we find is that we can only put lower bounds on metallicity because all the spectra are flat. So that is not what people find for K218b or TOI270d, that is GJ9A27 or 6D. Anyway.
Zip code.
Anyway, but yeah, in our program, this is what we find so far. And so we're putting these boundaries of it's at least 200 times solar. It's at least 300 times solar. And when we say that, this value comes just from the sheer fact that there is noise, and when we run a physical model, it's like, well, the noise is at least at that level. And so I'm not allowed to say what are the results of the 6 remaining planets, but without asking my colleagues, but let's assume that all 12 planets have flat spectra. Just as a thought experiment. What do we do next? And before I ask for the question, actually, so like this is the way these 12 targets were selected was to really focus on subneptunes that are at or slightly above the 50% water line. So they were selected to be different in mass, different in radius, different in equilibrium temperature, and they are 2 pairs of planets that are in the same system. So really, we're probing a very large parameter space. So we can talk about hazes, clouds, and other processes, but yeah, imagine all of them are flat. So first of all, does that mean that, okay, we solved pebble drift in the nebula? Does that mean that and if so, where do we move next? Does that also mean that we have, is this supposed to be like a general picture? Are we changing our perception of subneptunes?
Response and question, Lauren Weiss, University of Notre Dame. I'm so glad you mentioned TOI 270D. That was one of the things I wanted to bring up this session. And part of my question is, why aren't we talking more about that? Because that's one of the subneptunes where we actually have a non-flat spectrum in the atmosphere, right? That it's an M-dwarf star with a sub-Neptune planet with detected water features. And if I remember correctly, my ADS wasn't loading for some reason. Eduroam is blocked up or whatever. But if I remember correctly, it's also methane poor, right? So M-dwarf, which should be our friend that has the sooty soot in the disk, and yet the planet has water in the atmosphere and an apparent absence of methane, which might mean the methane is like sequestered deeper in the planet. But like, can we tie all of this together, M-dwarf, sooty disks, and TOI 270D into a self-consistent story?
Maybe.
So yeah. If I may, just TOI 270D, it has features, but that indicates a 100 times solar metallicity atmosphere. So it's visible, but the mean molecular weight is 6, a little bit higher than 6 gram per mole.
Yeah, because it's the water and hydrogen that are miscible.
Yeah, I mean, so if the way the solar system formed is uniform, then you would have carbon poor inner regions where all this stuff, you would have less ability to make the methane, right? Then the question is, okay, is that true of other systems? And so we have to figure that part out. And maybe the Ephiores that are over there destroy all the carbon because the carbon gets broken apart and doesn't get reconstituted, but the water does. So the water could refreeze after a burst, say, but the carbon goes into smaller things. And so if everything gets frozen and you make planetesimals in that phase, then you'd have less carbon in the planetesimals to communicate with. And so that's one thought construct that one can do, as long as you stop drift from the outer disk from feeding more carbon in.
Sorry, can FUREs be envelopes?
Yes.
Yes, yes.
Actually, a large fraction of the ones I've measured masses for seem to be.
Yeah, so it's possible, but a bunch of things have to happen.
So back to Artem's question, I'd say the easiest way, two easy ways to get flat spectra are to make hazes, which is easy to do in a hydrogen-dominated atmosphere, especially if you have a lot of carbon in it.
Yeah, that's right.
Or a high mean molecular weight atmosphere, which means that the hydrogen-dominated atmosphere model for subneptunes might not be correct, right? So maybe, and my argument would be it's a balance of both of those things.
Yeah, but again, across all the parameter space.
Well, the parameter space we're looking at, which is all
yeah, which is pretty small.
Planet's close to the star, right? So yeah, yeah. I mean, one of the things we showed in an earlier paper was that if you have this carbon content in the atmosphere, it can actually overwhelm the thermochemical expectations. And so you could actually still have the hazes being formed even in conditions where you would think that methane would not be the, because there's no oxygen to run around with. Yeah.
So 270 is a multiplanetary system. So going back to Eric's comment, right? So why don't we do a comparative study? Has it been done? You know, has there been a proposal, HST or JWST, to observe B and C together and compare the two? And I think
yeah.
TRI 270 B and C.
Yeah. Exoplanet folks.
Yeah. Okay. So on the, I don't know about TI 270 for the multi-planet thing, but of course, multi-planet comparison. You're speaking my language. Thank you. But also, I guess reflecting on Laura's comment or someone else's comment about like the parameter space in which we're seeing these flat hazes. I've been thinking a lot about super puffs recently. Another thing we have not like talked about a whole lot yet at this conference, right? So the super puffs, and for instance, Kepler 51, some of them have some James Webb spectra. Those are all flat. And that's weird because we know that, right, these are things that are like a couple of Earth masses and the radius of Saturn. They really should have very large atmospheric scale heights. So one possibility is this like detached photochemical haze, which I don't know, maybe it's like a lot of carbon. So is the answer here super puffs are carbon-rich planets? These are planets also generally that are at pretty cold orbits, like outward of 100 days. So they could maybe support that. Of course, there are other explanations possible for the super puffs, but I'm interested in the simplest unifying theory.
Yeah, we have a JWC expert.
I was about to comment on that.
You go. I was going to release a bit different.
Okay, Artem, go ahead. And then I do want to make sure we get to Anjali's comment and then over here in 5 minutes.
Very short answer is that I have heard that the RV signal has some weirdness for superpuffs, so the masses could be revised to be actually higher and making them not superpuffs anymore. There are some TTVs in the RV. Sorry.
Right,
these are TTV-derived masses, right?
That's a conversation to have.
Yeah, let's move on. Okay, go ahead.
Anjali Piet, University of Birmingham. I have a very related question that may have been partly answered already, but this kind of reminds me, all the carbon and oxygen discussion reminds me of what we've been guilty in atmospheres of doing in the past, of saying, oh, let's measure the situ ratio of the atmosphere and it'll tell us exactly where it formed in the disk. And I think we know that that's a bit of an oversimplification and there's a lot of other stuff going on. As we go to smaller planets and these kind of soot or diamond situations, what are the things that we should be cautious of and the extra complicating factors in the disk, such that when we interpret
the atmospheres of these smaller planets, if we assume that we can measure the composition really well with JWST, which is, is challenging, and if we account for all the atmosphere-interior interactions, which is also complex, but if we kind of pretend that we can do that, yeah, what are the complications in linking that to the disk and the formation scenario beyond, snow lines and things like that?
The phases of the carbon is one, right? So we're making assumptions about the carbon content based upon the meteoritic IOM, which is for every 100 carbon atoms, there's 77 hydrogen and 16 oxygen and 2 nitrogen. So that's what we're assuming. And then we're making some leaps as to what phase that carbon would find itself in. And so that's one. But, that's the kind of stuff that more laboratory work and so on. So that's, again, conversations with the geo side.
Yeah, I don't disagree. We need more experiments. I don't do experiments, but we sure need more of them in wider phase spaces. But yeah, I think there's so many processes by the time you look at a planet's atmosphere that have gone into setting its composition. Mm-hmm. It's really hard to answer what is the constraint that gets you back to planet formation. But let's get this last comment in here.
I have a related question to that. Given the apparent potential controversy in the exact composition of our own outer planets, how do we overcome that challenge in our own neighborhood when we look at directly imaged planets and for their C/O ratios, and the fact that apparently all the JWST planets we're looking at have clouds that are obscuring our ability to actually tell their composition? I know it's the compositions that you can derive are sensitive to your assumptions about how efficient circulation is and equilibrium chemistry, and whether it's in equilibrium. Are there thoughts on moving forward, how to overcome that for transiting planets? Or is there something about the fact that they're close in that's making them more likely to produce hazes and stuff like that obscures our ability to study the atmosphere?
Well, I can answer the direct detection part, right? What we're seeing in the direct detection planets is very high metallicities and stellar C/O ratios. And these are all around A stars, and we have multiple A stars where we have C/O ratios measured. And they're greater than ISM, what they should have formed out of. So if they're greater than ISM, and the CO is depleted, which is an observational statement, then all the carbon and the oxygen is in the solids. And if these things have metal-enriched atmospheres, it had to come from the solids. So that's useful information. The problem is the models don't work. Right? You can't accrete 100 Earth masses of pebbles and planetesimals. So there's a problem, but it's the challenge for your generation to figure out.
I'll say, one thing I love about about exoplanets and all of this new disk work is also the possibility of seeing young planets at different ages and pushing down to the really young planets and figuring out how those are different than the old systems like us.
I'll just as a comparative statement that the young directly imaged planets are the ones where you are most likely to actually be seeing their bulk composition because they're hot, so they're more likely to be well mixed.
So I think there are a couple of pathways to better characterizing atmospheres. One thing that we have not talked about much, which is the high-resolution spectroscopy from ground. I think that's highly complementary to space-based observation, mainly because the line that you see from high-resolution spectroscopy actually arises from the top of the atmosphere. So sometimes you can overcome a haze or cloud effect by going to high resolution. And the other pathway, I think, is from JWST wider wavelength coverage, going beyond the CO. For example, if you can see nitrogen and the sulfur, then maybe you could have a more comprehensive understanding or interpretation of the atmosphere. So I think the future is bright. I'm I'm more optimistic. I'm on the optimistic side.
I mean, NASA may be a crap show right now, but the ELT is being built, and it will have a high-resolution spectrograph, and it will do fantastic things for M dwarfs.
Well, I think on that very optimistic note, I think we're at 5:30 and it's time for our reception. So thank you to all of the speakers today.
Yeah, so we'll have the reception and then, of course, the dinner. And then we will regroup again tomorrow morning at 9 a.m. after the dinner for more planets and more JWST, of course.